Okay, hello sir. So today I'm doing term project map 241 and my topic is a chapter 3 review question, just like Sigma. I'm gonna do 10 questions and the question will start from 2, 4, 6 until 20. So the first three is 2, 4, and 6 have the same metric A and B. So A is a 2 by 2 and B is a 2 by 3 metric. And to compute the indicate metric impossible. So 2 is A squared times B. Since A squared can be written as A times A, so A square is a 1, 2, 3, 5 times 1, 2, 3, 5 here is a 2 by 2 times 2 by 2. The answer must be 2 by 2. And we do it in the multiplication way. It's a first row, first column here. So it's 1 times 1 is plus 2 times 3 is a 7. 1 times 2 plus 2 times 5 is 12. So we do it again with the second row. Is a second row, first column, second row, second column. Is the answer here. And then we do it A square times B and A square is here. So B is given. So A square is 2 times 2 by 2 metric time B is 2 by 3 metric. So the answer might be 2 by 3. And here is the answer. We do it by using the multiplication way. So move to the number 4 is a B power T times A inverse times B. So since B is a 2 by 3 metric, then B power T is a 3 by 2. Is we switch the column with row. So here is a first row become first column, second row become second column. Is A while A is a 2 by 2 metric, we can find the A inverse by using the determinant. So the determinant of A inverse A is a 1 times 5 minus 2 times 6. This is 1 over determinant here. And we got this minus 1, remember here. And we have the split position with 1, 5 here. Uh, and then we add negative to 2 and 3. And then it's minus 1, so minus 1 minus 5 is minus 5. Is 2 minus 3 become 3 and 1 become a minus 1. Then we compute the B power T times A inverse is possible because it's 3 by 2 times 2 by 2. So the answer must be 3 by 2 here. And then we know that B power 2 times A inverse is the answer here and B is given. So it's 3 by 2 times 2 by 3. So the answer might be 3 by 3 here. 6. The B power T times B inverse. So first let's find B power T times B, and we know that from the exercise for B equal here, and here is our B power T, and then B power T times B is possible because B power T is 3 by 2 and B is 2 by 3. The answer might be 3 by 3. Since it's 3 by 3 metric, we can find it inverse by using Gauss-Jordan elimination. So here we can write that is B power T times B here, and here is E. So we have to do the row to use echelon form at the last metric here. So we add air2 plus 9 over 13 air1 to second row, and air3 minus 10 over 13 air1 to third row. So we get E, and then we do it again on third row is air3 plus 66 over 36 air2 to second third row, and then we got it 0 here. Since the last metric is 0 row in it, I can say it also linearly dependent. So the B power T times B inverse does not exist. So move to exercise A. So if A is a metric such that A inverse is 1 over 2 minus 1 minus 3 over 2, 4, then find A. So by theorem 3.9, we can write that A inverse equal to A. And then so that the determinant of A inverse is 1 over 2 times 4 minus 1 times minus 3 over 2. Here is 1 over 2. So the determinant is 1 over 2 here, and then A equal 1 over 1 over 2. So it must be 2 here. And then we switch the position and add negative, and then we get the answer here. Move to the exercise 10. So if possible, express the metric A 1, 2, 4, 6 as a produce of elementary metric. Let the row reduce echelon form of A, and then it's a 1, 2, 4, 6. We add air2 minus 4 to second row. You got here. And then add the time 1 over 2, negative 1 over 2 AR2 to the second row. Then we get 1. And add AR1 minus 2 AR2 to the first row. And then we get 1 here. It's a row reduced echelon form. So then we got E1, E2, and E3. And how we know that E1 is 1, 0, minus 4 is 1. So E1 is here, is E2, and E3. And how to find E1 is we use the row reduced echelon form and use this. And we know that is add to second row. So AR2 minus 4 AR1. So AR2 is 0, minus 4 AR1 is minus 4. Minus 4 add to second row here is minus 4. So the answer will must be 1, 0, minus 4, and 1. And we do it the same with E2 and E3. And then we know that if E1 times E2 times E3 times E2 times E1 times A equal to E. When multiply both sides by E3, E2 times E1 inverse, then we're gonna get A here. So when you multiply here, and then you get here is E, and then here is the answer, and since E we can equal to 1, so we don't have to write it again. So since E1 here, we do the inverse by using the terminal, and here we got the answer E1, E2, E3, and then we write it again as this format is A before E1 minus E1 inverse times E2 inverse times E3 inverse, and here the answer here. Let's move to the exercise 12 is from the 3.4. So find the LU factorization of A. So first thing we have to know that A equal to L times U, and L is we have the leading one here. You have to remember this one, and you have to find L21, L31, L32, and to find U, we need to make this number here that the LU place becomes to 0. So and we don't care about here number. It doesn't need to be 1. Okay. So move to here. The row is 1 here. I do the row reduce echelon form. I add AR2 minus 3 AR1 to second row. AR3 minus 2 AR1 to third row. We got here. Then the one to make this number come to 0. So AR3 minus 3 over 2 AR2 to the third row. Then we got 0. Notice that we do this with the L. So here's L21. So here's L21, we do with AR2 and AR1. L31, we do it with AR3 and AR1. What here the same. L32, we do it with AR3 and AR2. If you do it with AR3 and AR1, it must be wrong. So I remember that. And here is U, how we know it is 3 is the opposite of coefficient here. So minus 3, the opposite is 3. Minus 2, opposite is 2. Minus 3 over 2 is 3 over 2. Though the final answer is L, here we add here 3, 2, 3 over 2. And U is find after you make this number become to 0. So move to the exercise 14. Suppose that a matrix and A and B are row equivalent. Do they have the same row space? Why or why not? Do A and B have the same space column? Why or why not? Based on the theorem 3.12, 20, let B be an matrix that is row equivalent to an A matrix. Then row A must be equal to row B. Row B equal to row A. Sorry, sir. So, however, the column space will not be the same. Let me give you an example. So let A equal to 1, 0, 0, 0, 1, 0, 1, 0, 0, 0. So, and we add AR1 minus AR3 to third row. So we come to 0. And we know that A and B is row equivalent. But column A span is 1, 0, 1 and 0, 1, 0 here. But B is 1, 0, 0, 0, 1, 0. It's same here, but here is not the same. And move to the exercise 16. If A is a square matrix whose row add up to 0 with the explain why it cannot invertible. So here, give you an example. It's a zero row here. So I can say it's linear dependent. So based on the theorem 3.27 here, the invertible must be the column vector is of A are linearly independent, and the row vector of A must be linearly independent. So since here is not linear independent, so uh, if the matrix who has the zero row cannot invertible. So move to the exercise 18. Find the linear transformation R2 to R2 such that T uh, 1 here equal to 2, 3, and T1 minus 1 equal to 0, 5. So the metric of T is T, and we can write as here TE1 and TE2. And we know that E1 equal to 1, 0, and E2 is 0, 1. So we can write that E1 and E2 as a linear combination of 1, 1 and 1 minus 1 here. Then we have E1 equal to 1, 0, and I let my coefficient is x and y, and E2 then the coefficient is a and b. Then we write E1 as a matrix, and then we have 1 plus 1 is equal to 1 here, 1 minus 1 equal to 0 here, and then we got x equal to 1 over 2 and y 1 over 2. When we do it the same with E2, and then we got a equal to 1 over 2 and b equal to minus 1 over 2. So I can write the span as the format, and then I add the transformation on both sides. So I got here, since 102 is a coefficient, so I can bring him here in front. And we know that t uh 1 1 and t1 minus 1 is already given, so we plug in here, and we end up is a 1 4. We do the same with SE2, then we get E here the E2. Oh, I'm sorry, sir. We do it the same as E1. Then we get the E2 here is a T01. So the answer might be 1 minus 1. And then the final answer of linear transformation of T is T equal to 1 for 1 minus 1. So the last exercise is a bit complex, I think. Suppose that A, suppose that T air power n to air power n is a linear transformation, and suppose that v is a vector such that t of v does not equal to 0 and t power 2 of v equal to 0, where t power 2 is t times t. Prove that v and t of v are linearly independent. Suppose that av a times v plus b times t of v equal to 0. Then if we want to prove that v and t of v are linearly dependent, only if a and b equal to 0. So we remember that to prove that it is a linear independent, we have to make the coefficient equal to 0, and our coefficient is a and b. Since t is linear and t of v power 2 equal to 0, then I can write here is TAV. I add the transformation both sides. So TAV here and TBGV and equal to since A is coefficient, we can bring him here. AT of V, also B and BT T of V. Then we got the T sum T is a 2T square. So it's a TV plus B T square of V. And we know that T is 0. And then A times T of V equal to 0. So A equal to 0 is true. Why? Because T of V does not equal to 0. And then we plug it in. Since A of V, we use this equation. So A of V, A equal to 0. And then V must be 0. So we had to remain the B time T of V equal to 0. And then B must be 0. Why? Because T of V cannot be 0. So since A and B are equal to 0, then V and T of V are linear independent. Thank you, sir, for your time watching this video. And that's all of my presentation. Bye, sir.